Welcome back. In this lesson, we are going to understand what is entropy, what is information gain, and then we are going to implement these two concepts in Python. But first, let's discuss what is a decision tree. Basically, we want to make a decision, right? And we want to make this decision based on questions and answers. So we want to classify a specific input, for example. So in order to classify this specific input, we are going to ask some questions and then we will get some answers. And based on these questions and answers, we are going to make a decision. So just like real life. So to understand better what I'm saying, let's go and see the final output of the decision tree for this section. So let's see. So here we are. We will understand how we can perform all this and how we can get this graph in a future video. But for now, let's understand what do we have exactly in this graph, right? So as we said, we have some variables. For example, we have educational number, capital gain, age, and so on, right? So for any input, we want to know if the class is 0 or if the class is 1. So first, we need to know what is the most important question for our classification or for our prediction. So here, as you can see, the first node of this tree or the first level for this tree is based on the merged status, right? So here, as we can see, if it's less than 0.5, and we will see how we can transform this into numerical, from categorical to numerical. But for now, let's say we will transform it, right? And we will go in this direction if the answer for the question is no, right? The answer is false. We will go in this direction. And if the answer is true, then we will go in this direction, okay? Then we will ask another question. Is the capital gain for this specific person less than 7,139 or not? If yes, then we are going to ask about the educational number, and then we are going to ask about the age, and then we are going to ask about the work class, and so on. So we will make our decision based on the answers we get on these questions, right? So we will ask a question for a specific feature or for a specific column, and the answer for this question or the value for this question or the value for this individual for this specific feature will help us make a decision if the classification should be 0 or it should be 1. So your question might be right now, what is the criteria or how we can calculate first the most important answer and how we can make this split? So why we are saying 0.5 and why we are saying here 12.5 and why we are saying here 8.5, right? So these are very, very valid questions. And we will answer all these questions right now. But the most important thing to know here is that the final output should be something like this. So this is a tree, as you can see, and we make the decision based on this tree, hence the name decision tree. So we are trying to be more and more confident by answering these questions and by going a little bit deeper in the decision tree, right? So as you can see, if we zoom in again, as you can see, we have something here called entropy, right? So this is the criteria which we are using to decide the most important feature. So right now we will go back to Google Colab and see what is the entropy, what its equation is like, and understand better the math behind it and try to implement it. So let's go. So here we are. Basically, this is the graph for the entropy. So the entropy is basically a quantity that we calculate in order to decide the factor of surprise, right? Or the added information in our system. For example, if I tell you that I have a coin, and this coin, of course, has a probability of being tails 50% and the probability of being heads also 50%. So if I flip the coin, right, the entropy is 1 because both of them are equiprobable, right? But if I give you some kind of strange coin, right, and this coin has a probability of being heads 100%. So both sides of this coin are heads. So in this case, if I ask you beforehand, how much are you going to be surprised when I flip the coin? You will tell me I will not be surprised at all. So the maximum surprise will be when there is a probability of 0.5, right? So that's why, as you can see here in the entropy, will be 1. This is the maximum entropy in case of two classes, or heads, tails, or 0, 1. When the probability for 0, or the probability of heads, is equal to the probability of tails, or the probability of 1. So this is the maximum entropy. And then, as you can see, this graph is symmetric, because when the probability of the heads is 0.4, then the probability of the tails will be 0.6. And this idea of entropy is actually used in communication systems. It's used in many fields, and it was first quantized and mathematically founded by Shannon in the last decade, right? So this is the idea of the entropy. The equation for the entropy, it's negative the summation of, like if you want to get the entropy of x, some event x, we are calling it here pi, but let's say x, then it will be negative the summation for x log 2 of x, right? So this is the equation. We will not dive deep in the mathematics, but this is basically the equation of the entropy, right? And of course we understand now the concept of the entropy. So the entropy is maximum when all the events are equiprobable. If we have 3 class variable, for example, then it will be maximum when each of them has a probability of 33.3, right? If we have 4 classes, then the maximum entropy will be when we have 25% probability for each class, right? So this is the concept of entropy, and we will see now why it's important for decision tree. But first, let's try to implement the entropy. So here I have a function called entropy, and the input for this function is basically a list of class labels, right? Zeros and ones. So here we have zeros and ones. And the output should be just a number, a value corresponding to the entropy for this list. Okay, so first we need to handle extreme cases or edge cases. If we have only one variable or only one value in this list, right? In this case, the entropy will be 0, right? If we have just one class, like I said, the entropy will be 0. There is no information, there is no surprise. We know beforehand it's going to be 0. But in case we have more than one value, then we are going to calculate the entropy. So how we can calculate the entropy? So as you can see here, first, if the length of class y less than or equal 1, then this function will return 0. And we are done here, right? But in case we have more than 1, then we are going to use a function in NumPy called bin count. So what this function does is basically, let's say here we have 1, 2, 3, and then 1, and then 5, right? Now, if we print numpy.binary count, so if we read the documentation here, it's saying count number of occurrences of each value in array of non-negative integers, right? So it will count the number of occurrences. So if we just give it x, you will see that we have 0, 2, 1, 1, 0, 1, right? So what does this represent? First, it starts from 0, right? So we don't really have any zeros. So the count of zeros will be 0. The count of 1, how many ones we have? We have 2 ones. So that's why we have 2 here. And then we have 1, 2. We have 1, 3, 0, 4. And then we have 1, 5. So that's basically what this function is doing. And we don't really need to do any extra work. We don't really need to take care of minimum value of negative values, because in our case, in our implementation, we only have zeros and ones, right? So if we have here 0, 0, 1, 1, 1, 1, this will return 2 and 4, because we have 2 zeros and we have 4 ones. So this is the total count. It will return a list, right, that contains 2 numbers. The first number will correspond to the count of zeros, and the second number will correspond to the count of ones. Then what we are doing here is that I am trying to find the probabilities. So how we are going to find the probabilities? Let's call this z, right? Now, if I come here and write z dot nb non-zero, okay, and I give it z, you will see that we have 2 and 4, okay? So let's first, in order to understand what we are doing, let's call the function called nb non-zero. So if we do so, you will see that we have 0 and 1. So it's returning 0 and it's returning 1. So if we read the documentation for this function, as we can see, we are giving it the count. So we have a count of zeros and we have a count of 1. So why we are doing this? Why we are doing this line? Because in case we have here 1, 1, right? Then this will return only one number. Why? Because if we print z here, you will see that we have 0 and 6. We don't really have any zeros, so the count of zeros is 1. So when we write nb.non0, this will return nothing, right? Because we are getting only the indices for the non-zero elements. Okay, so that's why we are writing this line, because in this case the entropy is also 0. Because if I tell you that the first time will be heads, the second time will be heads, the third time will be heads, so each time we have heads, then the entropy is basically 0. Okay, so after that, after we write this line, right, so we are getting the indices of the non-zero elements, we are dividing by the length of the class y, right? So what we are doing here is that if I take this, right, and come here, and here we have, this is, we called it z, and this is called that, right? So we have only one number, right? And we are going to divide by, the length of x, right? So as you can see, we have 1. The probability is 100%. But if we have here 0 and 0, and we have here another 0, so we have 3 zeros and 3 ones. So in this case, we have a 50% probability of zeros and a 50% probability for the ones, right? If we have here 1, then we are going to have 0.33 probability for zeros and 0.66 probability for ones. Okay, after that, as you can see, handling if the length of the probabilities is less than or equal to 1. So if we have here the length of probability, the length of this variable is 1, then we are going to return 0. So when it's going to be 1, it's going to be 1 if we have only one unique value in our list, right, in our labels list. So like this. So in this case, we will return 0. Otherwise, we are going to return the equation for the entropy, right? So this is the equation for the entropy. As you can see, we have negative, right? We have here negative, and then we have summation. So we are going to use nb.sum, and then for this summation, we are multiplying by, which is the probability, as we can see, the probability times the log of the probability. So nb.log of the probabilities. Okay, and in order to find the total entropy over all the elements, we are going to divide by nb.log the length of all the probabilities. So basically 2, right? So here we have 2, and nb.log 2 of 2 will return 1. So this is in case we want to extend this code to work with non-binary scenarios. Okay, so this is the equation for the entropy and how we can implement it. And I will leave this source for you if you want to read more about entropy and go deeper into the mathematics for this equation. Okay, now let's now understand the information gain, because we are not really interested in the entropy. We are not interested in the surprise in case of the decision tree, because in the decision tree, the question we want to ask is that, okay, now we divide our data set based on this variable, right? And we got some value for this variable we want to split on, and we will see now how we can do so in the next lesson. But our question is that how much information we are gaining from this variable or from this split, right? We split our data based on some specific variable. So how much information we gained based on this? Like I am asking you a question, okay? And when you answer this question, your answer might be very, very important and it guided me, or it was not important at all and I still have the same problems I had before, right? So this is the concept of the information gain. So the information gain is based on the entropy. So that's why we explained the entropy and implemented. So basically the information gain is, so as we can see here, information gain of y given x. So the information gain of our labels based on or given that we know x. Okay, so it's basically x is the question you answered or the questions I answered. Okay, so it's basically the entropy of y. So what is the entropy? Entropy is the uncertainty. Entropy is the uncertainty, right? So this is the uncertainty I had before, okay, minus the uncertainty I had before given the information you told me, right? So the information minus the uncertainty of y given x, okay? So basically just like what I have said in a few seconds, I just explained to you that if I ask you a question, I have some amount of information. Let's flip it the other way around, okay? So I have some kind of uncertainty. Let's say that my uncertainty before you answer the question was 0.7. Let's say 0.7, right? Now, after you answer this question, my uncertainty is 0.6, right? The uncertainty should decrease. The entropy should decrease, right? And if it decreases so much, then this means that I gained so much information. So the information gain is the amount of uncertainty I had before minus the amount of uncertainty I have right now. Okay, so let's now try to see the implementation for the information gain. So the information gain has two inputs. Previous y, this is the distribution of the original labels, right? And the current y, the distribution of labels after splitting based on a particular split attribute and split value. Okay, and the output should be the information gain. And as we said, this is the equation for the information gain. It's the entropy of y minus the conditional entropy of y given x. So how we calculate the conditional entropy? The conditional entropy equation is right here, but this is a lot of mathematics and I won't honestly go deep into this mathematics because there are a lot of people who are taking this course who don't really want to go deep into the mathematics. But basically, the conditional entropy is basically the summation of the probability of y and x occurring at the same time times log probability of y and x at the same time over the probability of x. So this is the equation for the conditional entropy and we can implement it just like this. So this is another way to write the conditional entropy, right? We are going to loop over all the current y's or over all the splits and we are going to calculate the conditional entropy based on this. But if you notice here, I am calling the entropy function, right? So here I am calling the entropy function on y, using y, right? So current y is basically a list of two lists, right? So the first list, the first split or the left hand side, and the second list corresponds to the right hand side. And as we can see here, after we calculate the conditional entropy, we can calculate the information gain by getting the entropy of the previous y or y here, right? Minus the conditional entropy, okay? So you can just replace previous y with just y, right? So we will come here and write y and we can replace current y by x, right? So this is the same equation we have above, okay? And this should return the information gain. Now let's test our implementation for the information gain and for the entropy. So let's first test the entropy. We tested before, but let's test it again. So here we have 3 zeros and we have 5 ones, right? If you calculate it on your calculator, you'll find that the entropy is 0.95. Okay? And then let's test also the information gain implementation. So here we have previous y. So this is the predictions I will make before you ask the question. Okay? And these are the predictions I will make after you ask the question. Okay? So this is before and this is after. And as you can see here, if we merge this with this, we should have the previous y, right? So here we have 0, 0, and here I have 1, 1, 1, 0, right? So if I go to the left hand side of the tree, then the probability of being 0 is 1, right? Because it's either 0 or 0. But if we go to the right hand side, 3 out of 4 we are going to predict 1, and 1 out of 4 we are going to predict 0. So that's why you are seeing that the information gain is 0.45. So the information gain number by itself, it doesn't really represent anything understandable, but when we compare the information gain after the first split, the second split, the third split, you will understand better what we are saying. Okay, so this is the implementation for the information gain and for the entropy. You will understand better and better in the next 2 lessons what do we mean exactly by the decision tree algorithm and how it works, and we will see where we are using this information gain function and where we are using the entropy function. So in the next lesson we will start understanding the decision tree ID3 algorithm. Okay, so let's go to the next lesson.